So in the last lecture, we discussed the parallel operation of two alternator, and especially we have discussed about the uh, effect of change in armature, effect of change in excitation at no load. So in this case, if two alternators are working in parallel, generator 1 or alternator 1 and alternator 2 both are working in parallel, which having resistance and reactance. So impedance 1 and impedance 2, they are supplying a common load. That is, they are supplying a common load Z1, Z2, IA1, IA2, and excitation EMF EF1 and EF2. So as soon as we increase the excitation of one of the alternators, say for the alternator 1, it is found that under such condition, when the two alternators are perfectly under parallel operation under no load condition, the EMF induced in each alternator is same, the magnitude is same, only it is opposite to each other in the internal one. So it is internal EF1 is equal to EF2, and as soon as we increase the excitation of alternator 1, its magnitude is get increases. Alternator 1 voltage is get increases EF1 dash, and because of this, local circuit voltage is developed, which is equal to say EC, which is the difference of EF1 minus EF2. Now this local circuit is dominantly inductive, so current is going to lag with EC. So here the current is lagging with 90-degree, and now we will give the name is as a IC. Now this current IC is lagging with respect to the EF, and IC is leading with respect to the EF2. So as per the armature reaction, the IC is produce demagnetizing effect for the alternator 1, and it will produces the magnetizing effect for the alternator 2. So because of demagnetizing effect, whose magnitudes get decreases, whereas for the alternator 2, where the effect is magnetizing, the voltage get increases. So one is decreasing, second is increasing, and again the two alternator voltages EMF induced become same, and as soon as these two voltages become same, the excitation, the difference of this voltages goes to the zero value, and current also. So here it is can be said that IC is the synchronizing current, whose function is to bring again two alternator into the synchronism. Once the two alternator again become synchronized to each other, or the voltages become each other, the current goes to the zero value. Okay. Now one more thing which we have to remember, that under such condition, say for example, the earlier before increasing the excitation of one of alternator, the voltage is equal to say 230 volt, but because of increase in excitation for any one of the alternator, the effective or the equivalent voltage, total voltage may increase say 232 volt or 235 volt. Okay, so there is a slight increase in EMF of two alternators. Now say this is the effect of armature, effect of change in excitation. The second part which we have discussed, effect of change in mechanical torque or mechanical power input. Okay, so mechanical torque we will say consider. So under such condition, two alternator voltages are same. Say two voltages are again same under before any increase in the excitation, but as soon as we increase the excitation for one of the alternator, so the voltage magnitude will remain same. Only one voltage or for the alternator 1 whose mechanical input has been increased advances in a phase. So this is advances in phase. Say this is EF2 and this is EF1. Okay, and because of this voltage, again this EC is going to develop, and this EC say this EC draw some current. Okay, so we will draw one more diagram for understanding purpose. Say this is the before increasing the mechanical input to any one of the alternator. Okay, so this is EF1 and EF2. Okay, so similar to the previous case. Now, once we increase the mechanical input to one of the alternators, say alternator 1, whose magnitude is remain same, only it is advances in phase. So here it is advances in phase. So this is the EF1 dash, isn't it? Magnitude is remain same. So because of this one, the resultant voltage or the vector addition, this is the voltage is going to produce. So this is the voltage is EC. Okay. Now, as this is the voltage and it is in the local circuit, it is only in the local circuit voltage, it will develop current is the synchronizing current or circulating current. It is lagging with the 90 degrees. Here it is lagging with the 90 degrees. So this current is IC. Now here the voltage EF1 and this current say theta 1 and voltage angle between IC and EF2, it is say theta 2. So we can say that EF1 IC cos theta 1 is positive because theta is less than 90 degree, and EF2 IC cos theta 2 is negative. So the first machine 1 is in the generating mode, is a generating, and second also second is in the motoring mode. So the machine which is in the generating mode, it is get retarded, whereas it is get accelerated. Okay, it is get accelerated. So one machine is retarding, second machine is accelerating. So the effective action is in such a way that both machine comes again into the synchronism and whose speed become constant. Okay, so here again the value of current IC is responsible to bring the machine again into the synchronism, and it is possible only when the circuit is inductive. Suppose the current, suppose the circuit is only resistive, the current in phase with the voltage, current also in phase with the EF2, and there is no generating mode and motoring modes are there, both are in the generating mode, and this synchronization will not be happen. So our conclusion is that under no load condition, either if you increase the excitation, because of increase in excitation, some current is going to develop, or some current that is called as a magnetizing current is going to develop in the local circuit. It will bring the two alternator excitation voltage again equal. And similarly, when we increase the mechanical input to one of the alternator, again some local circuit voltage is going to develop. This will drive the current, and the responsibility of the current is again bring to alternator in the synchronism. So this is the things which we have already discussed. Now we will see under load condition. Let the alternator is loaded. Let the alternator is loaded, and we are changing the excitation. Okay, so change in excitation we want to observe. So change in excitation under load condition. So in the previous section, we come to know this equation P is equal to EF Vt upon X into sine delta. Okay, or XS is the synchronous reactance is the sine delta. If you ignore the resistance of a synchronous alternator, if the power is constant, we can say that it will constant only when we can make the equation as xp upon ef is equal to vt sine delta. It means that if the power is constant, we can consider that vt sine delta may remain constant, isn't it? And we are going to change the excitation. So the excitation change, the change is going to observe in the uh, emf induced only. So for this one, first of all, what we will do, we will try to develop a phasor diagram under some particular load current, lagging current is there. Okay, so here, say for example, this is the terminal voltage. Be careful because it is very important and somewhat difficult as a first learner to understand. Say this is the terminal voltage Vt. Okay, now there is a current. Current is say lagging at an angle of theta. For our simplicity, it is current is for both alternator is IA1 is equal to IA2. IA1 is equal to IA2. They are supplying the equal loads are there. Therefore, the total current is twice IA1. Okay. Now, because of this one, the voltage is going to drop across the reactance, and it is represented as say it is I2 IA1 excess is equal to IA2 XS2. Okay. So XS1, XS2, and the total voltage is say EF. This is the excitation voltage EF, where both voltages are same. So EF1 is equal to EF2, and we will extend this value of current in such a way that this is the current IL is equal to twice IA1, or it may be twice IA2. Both our alternators are delivering equal current. So here generator 1 or alternator 1, alternator 2, whose reactance and impedance, and resistance, they are delivering the current IA1, IA2, excitation EMF EF1, EF2, and total load current is equal to IL, which is equal to either twice IA1 or twice IA2. So this is the load. So this is the ideal condition where two alternators are working in parallel, isn't it? So both alternators are working under such a parallel condition. Now whose power factor is, say, this power factor angle is theta. Power factor angle is theta. So it is working at power factor, both is theta. Now, our intention to examine what is the effect of change in excitation. Say, for example, we are increasing the excitation of alternator 1. We are increasing the excitation of alternator 1. So what happened? The magnitude of EF1 is going to increase. So here, this is going to increase in such a way that the part, which part? This part, say I will draw this over here. So this come here up to say, this is, what is this? This is nothing but this part is nothing but Vt sine delta will remain same. So this angle is delta. Okay. So now this is the new value of excitation 1, excitation EMF of alternator 1. So this is the case. Now we will represent as EF1 dash. Here it is IA1 dash XS1, and this angle is delta 1. This angle is delta 1. So for all values of EF into sine delta will remain, EF VT into sine delta will remain constant. Okay. So under such condition, what happened? The current IA1, current delivered by the alternator 1, IA1 get more lagging, and it is represented as, this is the current, this is the current, this is the IA1. So here IA1 get increase, IA1 dash will get increase, isn't it? Now this increase in IA1 dash, IA1 dash does not support the load current, whereas the load current will remain same, isn't it? And to maintain this one, we have to decrease the excitation of second alternator. We have to decrease the excitation of second alternator, or we will decrease the excitation of the second alternator. So what happened? Say this is the voltage EF2 dash, and this value is IA2 dash into XS2, and angle is theta delta 2, isn't it? So this will decrease the value of armature current. So we will have decrease in armature current in such a way that it is IA2, this current is IA2 dash, and the combination of these two in such a way that the total current IL will remain same. The total current will IL will remain same. So we found that by increasing the excitation and by decreasing the excitation, the load current will remain same. Load current will remain same, and similarly, the component of current in phase with the terminal voltage. In phase with the terminal voltage. Which component? This is the component. Which phase? So it is maybe IA1 dash cos theta, say this cos theta 1 and this cos theta 2. IA1 cos theta 1 is equal to IA2 dash cos theta 2 is equal to any current IA1 cos theta or IA2 cos theta, isn't it? So it means that the active component of current, try to understand, this is the voltage, terminal voltage, and this is the current IA1. Say for example, this angle is theta. So it has two components, one component in phase with the voltage. So this component is called as a active component. IA1 cos theta is the active component. So it is found that by varying the excitation, the active component of current will remain same. When the active component of will remain same, we can say that the active power delivered by generator will remain same. So there is no change in the active power delivered by that particular generator. One point. Second is that if you increase the excitation of alternator 1, it will deliver the current at more lagging power factor. So we can say that by increasing the excitation, that alternator supply more reactive power as compared to the other. Or we can say that the alternator whose excitation has been increased work on lagging power factor or poor power factor and supplies more reactive power, whereas the second alternator whose excitation kept constant work on improved power factor and supplies less reactive power. So finally, we say that by changing the excitation of the alternator, the reactive powered by two alternator may be altered, or the sharing of reactive power can be changed, whereas the active power does not change, isn't it? So there are two type of channel. One is the PF channel and second is the QV channel in the power system. So QV channel, it's whenever you are going to change the reactive power, the terminal voltage get changes. So here, because of this increase in the excitation, only two alternators are working parallel. So we can say that there is a slight increase or slight decrease in the terminal voltage. Effective terminal voltages are there, isn't it? So our conclusion is that conclusion number one is that whose excitation have been increased work poor power factor, work on poor power factor, supplies more reactive power, Second, whose excitation has not increased, it will work on improved power factor and improve power factor and decrease the share of reactive power, isn't it? So the total power will remain same. Power delivered by the alternator 1, active power delivered by the alternator 1, and active power delivered by alternator will remain same. So this is the meaning of change in excitation under load condition. Now, if you increase the mechanical input to one of the alternator, under such condition, suppose two alternators are working in parallel. Alternator 1 and alternator 2 are working in parallel, and here the mechanical input or mechanical torque has been increased in one of the alternators. Say alternator 1 mechanical input has been increased. So under such condition, it will supply more active power. And it will supply less reactive power, active power. So our conclusion is that if we increase the mechanical input or change in mechanical input, the generator or the alternator supplies more active power, and the second alternator will share less reactive power, whereas the reactive power will remain same. So in the concern is that if you want to change the reactive power delivered by alternator, we have to change the excitation, and when we want to change the active power delivered by the alternator, we have to change the mechanical input. So any change in mechanical input, there is a change in active power, and when there is a change in excitation, there is change in reactive power. So mechanical input, change in mechanical input, it is observed in active power delivered by that generator. Okay, and when we are changing the excitation, the change in excitation, so there is a change in reactive power. So the generator whose excitation has been increased, it will work on poor power factor and supplies more reactive power. And mechanical input, it will supply more active power, whereas the reactive power will remain constant. So under such condition, the change in voltage is observed. There is a slight change in terminal voltage is going to observed, whereas there is a change in frequency is going to observe. So this is the very important parameter, important discussion is that effect of change of excitation and effect of change of mechanical input. So if you summarize this one, if you change the excitation, active power will remain same, total active power will remain same. Only the reactive power shared by two alternator is going to alter. Okay. The generator whose excitation has been increased more, it will share more reactive power and work on poor power factor. Now, change in mechanical input. If you change the mechanical input to one of the alternator, it will supply more active power, and second generator will supply less active power. The total active power may increase slightly. Because of that, there is a change in frequency is going to observe. The frequency of the system is increases because here two alternators are working in parallel. So this is the change in mechanical input and change in excitation of two alternator when those are working in parallel.